Welcome back to the series of higher maths questions from the Leaving Cert 2008. We head for question 4, and the first part is a geometric series 2 plus 2/3 plus 2/9 plus etc. And we're asked to find the sum to infinity. Okay, we have the first three terms of a series. The idea is to find the series as a single expression in n and then take the limit as n tends to infinity, all the while hoping that it does actually converge upon a certain number. As it's geometric, we should search for the constant which is multiplied to the previous term each time. To find this out, we divide each successive term by the previous one, i.e. we take 2/3 and divide it by 2, or multiply it by a half and we get a third. We get 2/9 and we multiply it by 3/2 and we get a third again. So we recall the general expression for a geometric series, which is the sum to n terms equals a times 1 minus r to the n all over 1 minus r. Okay, so we've worked out that r is a third, and that the first number, obviously, a, is equal to 2. So we plug in these values to get our sum to n, and this is given as shown, and we eventually get 3 by 1 minus a third all to the n. And we've now expressed the series in terms of n, so we take the limit as n tends to infinity and see that it's the power of a third. So what happens to that term? Well, that term tends to 0. So we're left with 3. So our expression tends to 3. And the answer is 3. So that's part A. We go into part B, and we're given, again, an nth term of a certain sequence. And we're asked to write down the n plus 1th term and the n plus 2th term. So the first part is fairly straightforward. It hardly needs explaining. Just substitute n plus 1, for example, where n is. And the n plus 2th expression is also carried out in the same way. However, a little simplification is possible here by noticing that by pulling out a minus a half from the minus a half to the power of n plus 1 expression, we can cancel the 2's. So we're left with minus a half to the power of n minus 2. And we can take that expression again and use it on the n plus 2th expression, and that simplifies to a half, minus a half to the n minus 2. Okay, so this is going to be useful for section 2 of part B. So we're asked to show that twice the n plus 2th term minus the n plus 1th term and minus the nth term actually turn out to be 0. So we've already done some simplifications, and we can manipulate these to see if they are in fact 0. So we take the n plus 2th expression, which we've already found, and multiply it by 2. Then we take away the n plus 1th expression, which we've already found, and then the nth expression itself, which is the original term as given in the question. Now, we need to be careful with the signs, but it simplifies as follows. As given there, some easy simplifications can be carried out, and if you look carefully at this expression, it can be seen that all the terms cancel out. In fact, the form, if we take a to equal minus a half to the power of n, and then b to equal simply b, the form of that expression is a minus 2b plus b minus 2a plus b, which does in fact come out to 0, although the fractions make it a bit confusing, and it's clear they cancel out. So the proposition has been proved. So we move on to part C, section 1, and we're given the sum 1 plus 2 plus 3 all to n, and then 1 squared plus 2 squared all to n squared. Okay, now with any luck, these will not be strange series. You will have seen them before, hopefully. Okay, the first is actually the sum of all integers up to n, which Gauss famously used as a kid. And the second is the sum of all squared integers. It is possible to work these out, but in fact we are only asked to write down the expressions. So it's a question, as usual, of knowing the identities by heart. They are as follows. the sum of all integers up to n is n over 2 by n plus 1, and the sum of all squared integers up to n is n over 6 by n plus 1 by 2n plus 1. If you have an extra minute, inserting an easy number, such as 4, in these two equations will make you doubly sure that you have got the formulas correct. That's if you only you have some doubt as to whether you've remembered them properly. Okay, we go on to section 2 of part C, and here we're going to have to implement those expressions that we've just written down as requested, because we're given this sum, which is made up of 4 terms. Now we can distribute the summing notation into brackets. Okay, so each term will get its own summing notation. And we've already worked out the first 2 of these series of these 2 terms, because we can see r squared and r coming up there, which is the sum of all squared integers and the sum of all integers. And then the third term is actually 5n, and the fourth is the standard in a standard geometric form with a equal to 2, and we can rewrite it. We can rewrite this series of 4 sums as follows. That's the second term, the third term, and then the fourth term in the standard geometric format. Okay, now all that can be simplified, and now we're in the cycle of just trying to simplify and come out with a neat expression. And now we're asked to find the expression in terms of n, so we continue trying to manipulate these values so that a neater expression, a shorter expression comes out. Now we can continue expanding here, even though at this stage we have the majority of the marks because we've done as asked. The expression now is only in terms of n and some specific numbers. Okay, however, we will continue a little more, given that we may have an extra minute, and we see that 2n cubed plus 4n squared plus 7n minus 2 plus 2 to the n plus 1 is as simple as we can get it. In fact, it's almost further simplification is, and even this amount of simplification is pointless during the pressure of an exam. However, there is a cubic inside that expression, but in fact it does not turn out to have a neat solution, which is unusual for an exam, but you've got to allow exceptions to the neat solution view. And that is in fact the end of this question. Thank you for your attention.